Space is not just height, width, and depth. It may hold hidden dimensions, curled so tightly they escape our senses. These extra directions, invisible yet ever-present, could shape the forces and particles that build our universe. A radical idea born over a century ago, from ancient philosophers to modern physicists. This quest to uncover unseen realms reveals a cosmos far stranger than we imagine. A story of bold visions waiting for their time. The pursuit of truth often begins with a single insight, long before the world is ready. Over 2,000 years ago, a Greek philosopher named Democritus sat beneath the Mediterranean sun pondering the nature of reality. He proposed that all matter, stone, water, air, was made of tiny, indivisible fragments called atoms, eternal pieces combining to form everything we see. This atomic hypothesis was a leap beyond the era's belief in Earth, air, fire, and water as elements. It took 60 generations, well into the 1800s, for science to confirm atoms' existence, proving Democritus right long after his life had ended. His story is a quiet truth in physics. The boldest ideas often linger, their proof delayed by centuries. In 1783, an English clergyman named John Michell explored another frontier, studying Newton's laws of gravity and the idea that light was made of particles. He imagined objects so massive their gravitational pull would trap even light itself. These dark stars, as he called them, would be invisible, their escape speed exceeding light's swiftness. Michell's vision was a glimpse of what we now call black holes, but it was too far ahead, forgotten for 200 years. His idea resurfaced in the 1970s, when astronomers detected these cosmic voids. Like Democritus, Michell saw a truth the world could not yet embrace, a pattern in physics where revolutionary ideas wait patiently. These historical echoes frame our exploration of extra dimensions, a concept as daring as atoms or black holes. In 1916, Albert Einstein reshaped our view of the universe amid the devastation of the First World War. With Europe's youth falling in the trenches, he unveiled his general theory of relativity. Building on his 1905 special theory, which links space and time, Einstein showed that gravity is not a force but a curve in four-dimensional space-time, three spatial directions, and one of time. A star warps this fabric, guiding planets' paths like marbles rolling in a dip. The theory was profound, its mathematics intricate, its predictions subtle, yet it opened a door to new questions. One such question came from Theodor Kaluza, a mathematician from Silesia, a region now part of Poland, raised in Königsberg, a hub of German scholarship. Kaluza was immersed in the intellectual currents of the early 1900s. In 1921, he asked a radical question: what if space-time had not 4 but 5 dimensions? The three spatial directions we know, height, width, depth plus time, seemed complete. But Kaluza imagined a fourth spatial dimension, curled into a circle so small it was undetectable. This extra dimension, present at every point in space, would be like a thread surface, invisible from a distance, but real up close. Kaluza applied Einstein's equations to this 5-dimensional spacetime and found a startling result. The equations describe gravity in 3 dimensions, plus a force akin to electromagnetism, the force of light and magnetism. This was a unification, a single geometric framework for 2 fundamental forces, suggesting that the universe's complexity might stem from hidden dimensions. With Einstein's endorsement, Kaluza published his work in the Prussian Academy of Sciences. It was a visionary leap, hinting that the cosmos's rules could be written in the language of unseen geometry. Yet 1921 was a troubled time. Europe's scientific community, once vibrant, faced growing shadows as divisive ideologies took root. In physics, quantum mechanics emerged, a new frontier of particles and probabilities that captivated scholars with its testable predictions. General relativity, with its abstract curves, felt distant, and Kaluza's fifth dimension, unobservable and speculative, struggled for attention. The idea of extra dimensions, though profound, slipped into obscurity, a seed buried in the margins of science, awaiting a moment to grow. That moment began in 1968, a year of global upheaval, as protests echoed worldwide. An Italian physicist named Gabriele Veneziano tackled the strong force, the invisible bond holding atomic nuclei together. His solution was string theory, a framework where particles are not points, but tiny, one-dimensional strings vibrating at different frequencies. Each vibration produced a different particle: electrons, quarks, photons, offering a new way to understand the universe's building blocks. String theory was elegant, a cosmic symphony where notes defined reality, but it carried a heavy demand: 6 extra spatial dimensions, plus time, totaling 10. These extra dimensions were not vast like the space we navigate, but curled into realms smaller than a quadrillionth of an atom, present everywhere yet unseen. Veneziano's theory aimed to explain the strong force, but it faltered. Its predictions didn't match experimental data, and the need for 6 extra dimensions seemed a fatal flaw. By 1973, string theory was on the brink of abandonment, dismissed by most physicists as a beautiful but broken idea. The Standard Model, with its steady stream of particle discoveries, dominated the field, leaving string theory as a curiosity, its extra dimensions a puzzle too strange to solve. Despite this, a few saw potential in string theory's mathematics. Michael Green and John Schwartz, working through the 1970s, noticed patterns in the equations, cancellations too precise to be mere chance. They began to suspect that string theory's true purpose was not the strong force, but something grander, a quantum theory of gravity. This was a bold vision, seeking to unite Einstein's relativity, which governs stars and galaxies, with quantum mechanics, the realm of atoms and particles. Such a theory of everything had eluded physicists, a dream that seemed out of reach. In the 1970s, string theory was deeply unfashionable. The Standard Model's successes, new particles found nearly yearly, cast a long shadow, and the idea of extra dimensions felt like a relic of abstract mathematics, not physics. Green and Schwartz worked in near isolation, their belief in string theory a quiet defiance of the era's trends. They saw in its equations a possibility, a hint that the universe's deepest truths might lie in dimensions we cannot see, vibrating strings that weave the fabric of reality. Their persistence laid the groundwork for a turning point, a moment when string theory would rise from obscurity. The extra dimensions, once a barrier, would become a beacon, drawing physicists to a new frontier. Kaluza's vision, buried for decades, and Veneziano's strings, nearly forgotten, were seeds waiting to bloom. The universe, with its hidden geometry, holds its secrets close, but the human drive to seek them through equations, experiments, and imagination keeps the story alive, a narrative of truths that endure beyond their time. This journey through extra dimensions is just beginning. The cosmos, from its smallest fragments to its grandest scales, invites us to look closer, to chase the unseen. The ideas of Democritus, Michel, Kaluza, and Veneziano are not just history, but a call, urging us to seek the dimensions that may define our reality, a search that carries us from the past to the edge of tomorrow. String theory, with its 6 extra dimensions curled into realms smaller than atoms, offers a vision of a universe where tiny vibrating strings weave the forces and particles of reality. In the 1980s, this once-forgotten idea surged back to life, driven by a breakthrough that made it a beacon for physicists seeking a unified theory. The shapes of these hidden dimensions, intricate and unseen, hold the key to unlocking the cosmos's deepest secrets, a pursuit that blends mathematics with the human yearning to understand our place in the vast unknown. By 1973, string theory was a fading dream, its promise dimmed by mismatched predictions and the daunting requirement of 6 extra spatial dimensions beyond the 3 we know, plus time, totaling 10. Physicists had turned to the Standard Model, which reliably charted particles like quarks and electrons, leaving string theory's abstract dimensions in the shadows. Yet a few held fast, seeing in its equations a potential far grander than its initial aim. Among them were Michael Green and John Schwarz, who believed string theory could do more than explain the strong force binding atomic nuclei. It might unify gravity with the quantum world. Green and Schwarz, working through the 1970s, faced a field skeptical of extra dimensions. The Standard Model's steady discoveries dominated, and string theory's 10-dimensional framework seemed a mathematical curiosity, not a description of reality. Their work was a quiet rebellion, driven by the elegance of equations where unexpected symmetries hinted at deeper truths. They proposed that string theory strings, each a one-dimensional thread vibrating at cosmic frequencies, could describe not just nuclear forces, but gravity itself, quantized at scales smaller than atoms. This was a bold leap toward a theory of everything, a single framework for all forces and particles. The challenge was daunting. String theory's quantum calculations produced anomalies, errors where probabilities failed to align, rendering the theory inconsistent. These flaws were a barrier, a sign that the extra dimensions might be a mirage. Green and Schwarz, undeterred, labored in relative obscurity. Their belief in string theory's potential, a spark in a field dazzled by more immediate successes. Their persistence was a human story, one of dedication to an idea that seemed destined to fade, a reminder that physics often rewards those who wait for the right moment. That moment arrived in 1984, in Aspen, Colorado, a mountain town where physicists gathered to explore the frontiers of science. At a conference, Green and Schwarz presented a breakthrough that changed everything. They had found a correction, a term in the equations that erased the anomalies, making string theory consistent. This discovery, known as Green-Schwarz anomaly cancellation, was a turning point, a moment when the theory's 6 extra dimensions transformed from a liability into a promise. The physics community, once dismissive, turned its gaze to string theory, seeing in it a path to unify gravity with the quantum realm. The Green-Schwarz breakthrough was more than a mathematical fix. It was a revival. String theory suggested that the universe's particles, electrons, photons, quarks are vibrations of strings in 10 dimensions, their frequencies set by the geometry of 6 curled spatial dimensions. These extra dimensions, smaller than a quadrillionth of an atom, are present at every point in our 3-dimensional space, invisible yet shaping reality. The theory's elegance lay in its unity. A single framework could explain the diversity of forces in matter, from the pull of gravity to the spark of light. To understand these extra dimensions, physicists turned to geometry, a field rooted in the work of Pythagoras over 2,000 years ago. The shape of the extra dimensions determines how strings vibrate, thus defining the particles and forces we observe. In 1984, as string theory surged, physicists Andrew Strominger and Gary Horowitz sought specific geometries for these dimensions. They contacted Eugenio Calabi, a mathematician who confirmed the existence of Calabi-Yau manifolds. Six-dimensional spaces named for him and Xing-Tung Yao, a geometer whose work bridged mathematics and physics. Calabi-Yau manifolds are not simple shapes like circles or spheres, but complex structures, intricate as woven patterns, with topologies pierced by hundreds of higher-dimensional voids. These manifolds are critical because they satisfy Einstein's general theory of relativity in the extra dimensions, ensuring gravitational stability. A star warps four-dimensional spacetime. In string theory, Calabi-Yau manifolds maintain order in the six hidden dimensions, allowing strings to vibrate in harmony. This connection to Einstein's equations, first explored by Kaluza in 1921, gave string theory a foundation in the physics of gravity. Beyond stability, Calabi-Yau manifolds offer a deeper gift: supersymmetry. This conjectured property balances quantum energies, splitting chaotic effects into opposing forces that cancel, protecting the theory from instability. Supersymmetry is a shield, ensuring that string theory's quantum calculations remain consistent, a necessity in a world where quantum mechanics governs the smallest scales, though unproven. Supersymmetry's elegance captivated physicists, suggesting a universe where order emerges from complexity, a balance reflected in the manifold's intricate forms. In the 1980s, physicists dreamed that a single Calabi-Yau manifold would mirror the Standard Model, predicting the particles and forces we know. The hope was for a unique shape, a cosmic blueprint that would tie string theory to reality. But the dream grew complex. The number of possible Calabi-Yau manifolds exploded, from a handful to billions, each a unique geometry for the extra dimensions. Their names, quintic hypersurface, mirror quintic, carry an exotic allure, but their abundance posed a challenge: how to choose the one that defines our universe. This multiplicity is both a marvel and a puzzle. String theory's vision is one of unity, where a single framework births the cosmos's diversity. Yet the vast array of Calabi-Yau manifolds complicates the search. Computers now generate these shapes, their calculations far outpacing human hands, a testament to the theory's depth. The challenge is to find the manifold that matches our reality, a geometry where strings vibrate to produce the electrons, quarks, and forces we observe. This is a quest for precision, a search for the universe's hidden code. The human element in this pursuit is profound. The 1984 breakthrough was not just a triumph of equations, but a moment of connection, as physicists like Green, Schwartz, Strominger, and Horowitz shared a vision. Their work was a dialogue, a blend of mathematics and imagination, driven by the same curiosity that led Pythagoras to measure triangles or Einstein to curve spacetime. String theory's extra dimensions, though invisible, resonate with our need to understand, to see beyond the three directions we know, to touch a reality richer than our senses allow. The extra dimension scale makes them elusive, smaller than anything we can probe directly. Yet their effects may linger, like the atoms Democritus imagined or the dark stars Michel envisioned. String theory suggests that these dimensions shape the particles we observe, their geometry a silent architect of reality. The Calabi-Yau manifolds, with their supersymmetric balance, are not just abstract spaces but potential keys to the cosmos, their forms dictating the universe's laws. This search also carries a melancholic beauty. The extra dimensions, if real, are everywhere, curled into the fabric of space, yet they remain hidden, a reminder of our limits. The 1980s surge in string theory was a moment of hope, a belief that we might glimpse these realms, yet the challenge of billions of manifolds tempers that hope with patience. Physics is a slow journey, its truths unfolding across decades, as ideas once dismissed find new life in the hands of those who dare to dream. The story of string theory's revival is a bridge to the next step in our quest. The extra dimensions, with their Calabi-Yau shapes, are not the end but a beginning, pointing us toward the particles that may carry their traces. The universe, from its smallest threads to its grandest arcs, holds its secrets close, but the human drive to seek them keeps us moving forward, chasing the unseen dimensions that may redefine our understanding of reality. The extra dimensions of string theory, curled into intricate geometries, may leave their mark in particles that linger from the universe's birth, moduli. Elusive remnants of these hidden realms could hold the key to proving their existence, their faint presence a whisper from the cosmos's first moments. This search, blending the smallest scales with the vastness of creation, draws us deeper into a reality where the unseen shapes the world we know. String theory's 6 extra dimensions, smaller than a quadrillionth of an atom, are not just abstract spaces but active architects of reality. Their geometry, captured in Calabi-Yau manifolds, dictates how strings vibrate, producing the particles and forces we observe. These manifolds, with their complex topologies, ensure stability and balance through supersymmetry, a property that tames quantum chaos. Yet the challenge lies in finding evidence, a trace of these dimensions in the universe we can measure. The answer may lie in particles born of their geometry, particles that carry the signature of a 10-dimensional cosmos. Moduli are among these particles, unique in their role and nature. In string theory, they describe the size and shape of the extra dimensions, acting as markers of the Calabi-Yau manifold's configuration. Unlike electrons or photons, which spark and dance in our world, moduli are tied to gravity, the weakest of the universe's forces. This connection makes them both elusive and enduring. Their faint interactions a challenge to detect, but a clue to their persistence. Moduli are the ghosts of extra dimensions, their presence a potential bridge between the theoretical and the tangible. Gravity's weakness is a defining trait. Consider lifting a key ring with your finger, a simple act that overcomes the gravitational pull of the entire Earth, a force dwarfed by the electromagnetic interactions of your muscles. Moduli, behaving like gravity, are nearly invisible to our tools. Colliders like CERN's Large Hadron Collider, which smash particles to reveal new physics, cannot produce moduli. Their signals lost in the noise of stronger forces. Even neutrinos, which glide through Earth with ease, interact more readily than moduli, whose gravitational ties render them ghostly, fleeting, and faint. This faintness, however, is moduli's strength. Particles governed by stronger forces, like the strong nuclear force, decay in a yoctosecond, a billionth of a second, their energy fading into light and heat. Moduli, with their weak interactions, endure far longer, potentially for a microsecond, a brief but significant span in the early universe. This longevity makes them candidates to carry the imprint of extra dimensions, a signal from a time when the cosmos was young and its geometry was forged. To find moduli, we must journey to the universe's dawn, a moment of unimaginable energy. In its first instant, the cosmos underwent inflation, a rapid expansion that doubled its size 80 times in less time than light takes to cross an atom's nucleus. This explosive growth, transforming a speck into a vast expanse, ended with a surge of energy into particles. Inflation's energy, tied to the fabric of space itself, could have birthed moduli, particles linked to the geometry of the extra dimensions. In this primordial chaos, moduli joined quarks, photons, and other particles, a cosmic soup of creation. The early universe was a crucible, its particles a fleeting symphony, most driven by strong or electromagnetic forces, decayed almost instantly, their energy scattering into the growing cosmos. Moduli, however, lingered, their gravitational ties slowing their decay. As the universe expanded, relativistic particles like photons lost energy to the Doppler effect, their wavelength stretching like a siren's pitch, fading as it moves away. Moduli, heavy and slow, held their mass energy, resisting the expansion's pull. For a microsecond, they could have dominated, their presence a silent testament to the extra dimension's geometry. This epoch, though brief, is a window into the unseen. Moduli's dominance, if real, would have shaped the young universe's evolution, their mass energy influencing its growth before they decayed. This moment, lost to time, may leave traces in the particles they became, a legacy of the extra dimension's role in the cosmos's birth. The challenge is to find these traces, to detect particles so faint they seem to belong to a shadow realm, yet carry the weight of a 10-dimensional truth. The search for moduli is a human endeavor, rooted in the same curiosity that drove earlier physicists to explore atoms and gravity. The idea of extra dimensions, once a mathematical curiosity, now inspires experiments that push the limits of our technology. Moduli's gravitational nature makes them elusive, but their longevity offers hope. Unlike particles that vanish in an instant, moduli's microsecond lifespan suggests they could have left a mark, a signal preserved in the universe's vast archive, waiting for us to uncover. This quest also touches on the human experience of seeking the unknown. The extra dimensions, curled into every point of space, are a reminder of our place in a cosmos far larger than our senses can grasp. They challenge us to imagine a reality where the smallest scales hold the grandest truths, where particles like moduli connect the universe's birth to the world we see today. The pursuit of these particles is not just scientific, but deeply personal, a reflection of our drive to understand, to find meaning in the unseen. The melancholic beauty of this search lies in its scale. The universe's first microsecond, when moduli may have reigned, is a fleeting moment, yet its echoes could reach us across billions of years. This is a story of endings and beginnings, of particles that fade yet leave traces that endure. The extra dimensions, if real, are a hidden framework, shaping the forces that light our stars and bind our lives, yet they remain just beyond our reach, a quiet call to keep searching. The tools we use are extensions of this curiosity. Telescopes and detectors, designed to probe the faintest signals, are our eyes into the cosmos's past. The Large Hadron Collider, though unable to produce moduli, inspires new experiments, new ways to listen for the universe's whispers. These efforts, built on decades of theory, carry the legacy of string theory's revival, a moment when the extra dimensions became a frontier, not a fantasy. The physicists who pursue this path, those who followed Green and Schwarz's 1984 breakthrough, are part of a lineage, each step a move toward a truth that waits. The extra dimensions geometry, encoded in moduli, is a puzzle that spans the cosmos. From the curled spaces of Calabi-Yau manifolds to the particles born in inflation, this geometry may define reality itself. The challenge is to find these particles, to measure their effects in a universe that hides its deepest secrets. The story of moduli is a bridge to the next phase of our quest, a path toward particles that carry their decay, particles that might finally reveal the hidden dimension's truth. This journey through the unseen is a testament to human resilience. The extra dimensions, though invisible, are a call to explore, to seek the particles that may prove their existence. The universe, from its fiery birth to its silent expanse, holds these truths close. But the human spirit, curious, persistent, unafraid of the unknown, keeps us moving forward, ready to uncover the next layer of a reality that may be stranger and more beautiful than we ever imagined. Axions, faint particles born from the decay of moduli, may carry the echo of extra dimensions, a signal from the universe's first microsecond. These elusive remnants, streaming through the cosmos, offer a path to detect the hidden geometry of string theory's 10-dimensional reality. This search, pushing the limits of our tools, is a human quest to hear the universe's ancient whispers, a journey from the smallest scales to the vastness of time. Moduli, particles tied to the size and shape of string theory's 6 extra dimensions, could have dominated the early universe, their gravitational nature making them long-lived but faint. Their decay, a fleeting act in the cosmos's infancy, may have birthed axions, hypothetical particles nearly massless, with interactions almost as weak as gravity itself. Axions are not part of the Standard Model's familiar roster electrons, quarks, photons, but a shadow realm. Their existence a speculation rooted in string theory's vision of a 10-dimensional cosmos. If moduli decayed into axions, these particles could form a cosmic background, a faint sea persisting from the universe's birth to today. The universe's first moments, marked by inflation's explosive growth, set the stage for this possibility. As energy poured into particles, moduli emerged, tied to the geometry of extra dimensions curled smaller than a quadrillionth of an atom. Their microsecond reign ended as they decayed, potentially into pairs of axions, each carrying half the moduli's energy, speeding through space at near-light velocity. Unlike photons, which dimmed as the universe expanded, axions' faint interactions let them endure, a relic of the extra dimension's influence on the cosmos's dawn. Detecting axions is a formidable challenge, akin to finding a single whisper in a cosmic gale. Their interactions are so weak that they pass through matter-Earth. Stars, entire galaxies with barely a trace, even neutrinos. The ghostly particles of the Standard Model interact more readily, with experiments detecting a handful each year despite billions streaming through every cubic centimeter. Axions, if they exist, are even more elusive. Their cosmic background, a faint hum, estimated at hundreds per cubic centimeter, yet nearly invisible to our instruments. This faintness, however, is what makes them a beacon for extra dimensions, a signal untainted by the universe's later noise. The key to finding axions lies in their rare ability to transform. In strong magnetic fields, axions may convert into photons, the particles of light we can measure. This process, a delicate dance of quantum physics, offers a window into the unseen. Imagine a telescope peering through a magnetic field, seeking a flicker where none should be a photon, born from an axion, born from a modulus, born from the geometry of extra dimensions. This is not a simple task, but a frontier, requiring tools of unprecedented sensitivity to catch the universe's subtlest signals. Future experiments are rising to this challenge. Telescopes like the planned Axion Dark Matter Experiment, or ADMX, use powerful magnetic fields to search for axions, tuning their detectors to catch the faint photons they might produce. Other projects, such as the International Axion Observatory, aim to scan the cosmos for these particles, their instruments designed to listen for the quietest echoes of the early universe. These efforts, still in their infancy, build on decades of theoretical work, a testament to the patience required to probe the unseen. The search for axions is not just a technical challenge, but a human one, driven by the same curiosity that fuels string theory. The extra dimensions, curled into Calabi-Yau manifolds, are a mathematical marvel. their geometry shaping the strings that vibrate to form reality. Moduli, as markers of this geometry, connect these dimensions to the universe's birth, and axions, as their decay products, carry this connection to the present. The chain from dimensions to moduli to actions to photons is a thread through time, linking the cosmos's first microsecond to the tools we build today. This quest spans scales, from the microscopic curls of extra dimensions to the vast expanse of the universe. The Calabi-Yau manifolds, with their hundreds of higher dimensional voids, are realms smaller than atoms, yet their influence could ripple across billions of years. Actions, if detected, would be a signal from this geometry, a proof that the universe's forces gravity, light, matter stem from a 10-dimensional framework. This is a vision of unity, where the smallest scales hold the key to the cosmos's grandest truths. The human connection to this search is profound. We are beings of 3 dimensions, our senses bound to height, width, and depth. Yet we imagine more, driven by a need to understand our place in the universe. The extra dimensions, though invisible, resonate with this longing, challenging us to see beyond what we know. The physicists who design action experiments, who calibrate magnetic fields and analyze faint signals, are heirs to a legacy of curiosity, their work a quiet defiance of the universe's secrecy. The melancholic beauty of this pursuit lies in its patience. The universe's first microsecond, when moduli and actions may have formed, is a moment lost to time, yet its echoes could reach us today. This is a story of endings and beginnings, of particles that fade yet leave traces that endure. The extra dimensions, if real, are everywhere, their geometry shaping the forces that bind our world, yet they remain hidden, a reminder of the truths that wait just beyond our grasp. The tools we use are extensions of this human drive. Telescopes and detectors, with their intricate designs, are our eyes into the cosmos's past, seeking signals that have traveled since the universe's birth. The Large Hadron Collider, though unable to produce moduli, inspires these experiments, pushing the boundaries of what we believe possible. Each flicker of light, each photon detected, is a step toward a reality where the unseen becomes seen, where the extra dimensions reveal their role in the cosmos's story. The search for actions also reflects on the nature of discovery. Physics is a slow journey, its truths unfolding across generations. The idea of extra dimensions, sparked over a century ago, has grown from a mathematical curiosity to a frontier, driven by breakthroughs like string theory's revival in 1984. The physicists who pursue axions build on this legacy. Their experiments, a dialogue with the past, a conversation that spans decades and continents. This is a human story, one of resilience and hope, of seeking answers in the face of the unknown. The quest for extra dimensions, a century-long journey through hidden realms, reveals a universe woven from unseen geometries, from early visions to modern experiments. This search for a 10-dimensional reality reflects humanity's drive to uncover cosmic truths, a story of persistence and wonder. As we stand at this crossroads, we reflect on a narrative that spans the cosmos's birth to the tools we build, envisioning a future where the invisible becomes seen, where the universe's silent folds speak. This journey began with a question: what if space holds more than the 3 dimensions we perceive? Over a century ago, a scholar imagined a 5th dimension, curled so tightly it escaped notice, sparking a vision where geometry births the universe's forces. That idea, though buried for decades, found new life in string theory, a framework where tiny vibrating strings in 10 dimensions, 6 extra, hidden realms shape the particles and forces we know. The revival of this theory in the 1980s, driven by a breakthrough that tamed its quantum flaws, turned extra dimensions into a frontier, a promise of unity in a cosmos of endless forms. The extra dimensions, smaller than a quadrillionth of an atom, are not mere abstractions, but architects of reality, their shapes dictating how strings vibrate. These shapes, intricate spaces with complex topologies, ensure stability and balance, offering a glimpse of a universe where gravity and light stem from a single source. Particles called moduli, tied to the size and shape of these dimensions, emerged in the universe's first microsecond, their faint presence a potential clue to this hidden geometry. Actions, born from moduli's decay, may carry this clue forward, streaming through the cosmos as a faint background, a whisper from the dawn of time. The search for actions, using telescopes and magnetic fields to catch their fleeting transformation into light, is our latest step, a challenge that pushes the boundaries of what we believe possible. These experiments, seeking a flicker where none should be, are not just science, but a human endeavor, a testament to our need to know. The extra dimensions, if real, are everywhere, curled into every point of space, shaping the forces that bind our world. Yet they remain unseen, a puzzle that has driven physicists for generations. Reflecting on this narrative, we see a story of endings and beginnings. The universe's first instant, when inflation expanded it 80-fold, was a moment of creation, its energy birthing particles that may hold the key to extra dimensions. That moment, though gone, lives in the particles that endure, in the actions that might light our detectors. The physicists who pursued this truth, from the early 20th century to today, faced skepticism and silence, yet their ideas persisted. Each a seed that bloomed in time, their work is a slow dance, a patient unfolding of truths that wait for the right tools, the right minds, to reveal them. The human connection to this quest is profound. We are creatures of three dimensions, our lives bound to up, down, left, and right. Yet we dream of more. The extra dimensions challenge us to imagine a reality beyond our senses, to see the universe not as it appears, but as it might be. This is a deeply personal pursuit, one that resonates with our longing for meaning, for a place in a cosmos vast and strange. The scientists who build experiments, who sift through data for signs of actions, are driven by this longing, their work a bridge between the human and the cosmic. The melancholic beauty of this search lies in its scale. The extra dimensions, curled into spaces we cannot touch, are a reminder of our limits, yet also our potential. The universe's first microsecond, a fleeting spark, is lost to time, but its echoes could reach us, carried by particles that have traveled billions of years. This is a story of loss and hope, of moments that fade yet leave traces that endure. The extra dimensions, if they exist, are a silent framework, their geometry shaping the stars that light our skies and the atoms that form our lives. This narrative also reflects on time's passage. Physics is a journey across generations, its discoveries a tapestry woven by many hands, the idea of extra dimensions. Born in 1921, took decades to find its echo in string theory, and more to inspire the experiments we pursue today. Each step from a scholar's quiet insight to a breakthrough in a mountain town, from particles in the early universe to telescopes scanning the void, builds on the last, a legacy of resilience. The truths we seek, like atoms or black holes before them, may wait, their proof a distant hope that drives us forward. Looking to the future, the search for extra dimensions is a promise of discovery The tools we build telescopes with unprecedented sensitivity. Detectors tuned to the faintest signals are our eyes into the cosmos's past. Projects like the Axion Dark Matter Experiment and the International Action Observatory are just the beginning. Their efforts a foundation for what lies ahead. These experiments, seeking axions as proof of moduli and extra dimensions, could redefine our understanding, showing that the universe's forces arise from a 10-dimensional reality. The implications are vast. If axions are found, they would confirm the geometry of extra dimensions, a breakthrough that could unify gravity with the quantum world. This would not just be a scientific triumph, but a cultural one, a moment when humanity glimpses a deeper truth about existence. The extra dimensions, with their intricate shapes, would become more than theory, a reality that reshapes how we see the cosmos, from the smallest particles to the farthest stars. Yet the future is uncertain. The search for actions is a gamble, a hope that the universe's secrets will yield to our tools. The extra dimensions may remain hidden, their proof eluding us for decades more. This uncertainty is part of the journey, a reminder that physics is not just about answers, but questions, about the courage to seek what lies beyond. The universe is patient, its truths curled into spaces we cannot yet touch, but the human spirit curious, persistent, unafraid keeps us searching. This quest is a mirror to our own existence. We live in a universe of 3 dimensions, yet we imagine more. Our minds reaching for realms we cannot see. The extra dimensions, if real, are a testament to this imagination, a sign that the cosmos is richer than we know. They connect us to the universe's birth, to the particles that formed in its first moments, to the forces that shape our world. This connection, from the micro to the macro, from the past to the future, is a story of unity, a reminder that we are part of the cosmos's endless arc. As we conclude, we carry this wonder forward. The journey through extra dimensions, from a century-old question to the telescopes we build, is a human story, one of resilience and hope. It began with a vision of hidden realms, grew through the revival of a bold theory, and led to particles that may prove a 10-dimensional truth. The extra dimensions, though unseen, are a call to keep seeking, to listen for the universe's whispers, to dream of a reality where the invisible shines. The cosmos is vast, its secrets hidden in the folds of space, yet they beckon us, a promise that our questions matter. We are part of this narrative, our lives shaped by the same forces that vibrate in the strings of the universe. As we look to the stars, we see not just light, but possibility, a chance to uncover the truths that wait in the silent geometries of the cosmos. The search for extra dimensions is our story, a quiet vow to keep chasing the wonder that lies just beyond the edge of the known. In the beginning, there was no ticking clock, no sun to rise and set, no sense of before or after. Time, as we know it, was not yet born. Then, in a moment of unimaginable force and brilliance, the universe erupted into being, space unfolded, matter scattered. And with it, the strange and elusive current we call time began to flow. But from its very first breath, time has never been as simple as it seems. We tend to think of time as a reliable companion, always moving forward, never stopping. Seconds pass, minutes accumulate, and the hours stretch into days. It's in the turning of the seasons, the rhythm of our breath, and the growth of our children. We measure our lives by it, schedule our hopes around it. And yet, this companion we trust so deeply is anything but constant. Imagine a journey won not across countries or oceans, but across the very fabric of reality. You and your closest friend, once side by side, board separate spacecraft. Their ship accelerates, inching ever closer to the speed of light. You remain behind, watching the stars shimmer and stretch. From your vantage point, time begins to betray its uniform mask. Your friend's ship, once brisk and steady, now creeps forward as if wading through honey. Movements stretch like shadows at sunset. Voices drawl into distorted echoes. Minutes for them become hours for you. But inside the ship, your friend feels nothing unusual. Time remains their faithful ally, unwavering and steady. They sip tea, laugh at old jokes, watch the cosmos stream past, all unaware that from your eyes they are drifting into the slow ballet of time's dilation. This is no illusion. It's the heart of reality, unveiled by Albert Einstein over a century ago. Newton, centuries before, had imagined time as an absolute river, flowing evenly through all corners of the universe. But Einstein saw something deeper, more mysterious. He realized that time was woven into the very tapestry of space, and like fabric, it could stretch and twist, motion and gravity. He discovered were the hands that shaped it. Near massive objects, like black holes, gravity pulls at time itself. Stand close to one, and seconds extend like taffy. Move faster and faster, and time starts to yield, folding in on itself. This is why GPS satellites, orbiting high above Earth, tick slightly faster than our clocks on the ground. It's why astronauts return home a little younger than if they had stayed. These are not tricks. They are glimpses into the hidden nature of time. To truly understand this, we must journey backward back to the beginning. In the newborn universe, all matter and energy were crushed together into a searing, dense cradle. Gravity reigned supreme. In such a place, time crawled. The equations of relativity tell us this plainly. The stronger the gravitational field, the slower time flows. Imagine the first moments after the Big Bang as a frozen tableau, where the universe, still infant and fiery, pulsed in slow motion. Each second was thick with resistance. This warping of time, known as gravitational time dilation, is not confined to the past. It lingers. It governs the flow of time on planetary surfaces and in orbit, in collapsing stars and in the vast vacuum between galaxies. Time is not a universal tempo, but a local rhythm, changing with every step you take. And yet, motion plays its own game. Special relativity shows us that speed, too, slows time. A traveler moving near the speed of light will experience mere hours while centuries pass for those left behind. The twin paradox, a thought experiment turned physical law, illustrates this. One twin remains on Earth, living a normal life. The other soars through space at incredible speeds. When they reunite, one has aged, the other has not. This is not magic. It is the universe obeying its own rules. All of this challenges our senses, our instincts. We want time to be fair, equal, shared. But it isn't. It's shaped by where you are and how fast you're going. It is sensitive, reactive, alive in ways we never imagined. When we gaze at galaxies billions of light years away, we are not just seeing distance, we are seeing old light, stretched and slowed by the journey. Those ancient stars blink at us through the haze of history, their rhythms slowed by time itself. We measure this phenomenon as redshift, the elongation of light waves as they travel through expanding space. But behind this shift is a deeper truth. Time itself was different back then. Quasars, the brilliant hearts of early galaxies, flicker more slowly than their modern cousins, not because they were slower, but because the very universe was dragging time through the mud of expansion. To picture this, imagine a steep valley. At the bottom, near the black hole or the Big Bang, time flows like a sluggish stream. As you climb the slopes, away from gravity's grip or speed's embrace, the stream quickens. This graph of time versus position would not be a straight line, but a curve dipping and lifting, shaped by the contours of space-time. And this brings us to an even stranger frontier time travel. Not just forward, which we already accomplish in small ways, but backward. Here, paradoxes bloom. The grandfather paradox asks, what if you went back and prevented your own birth? The bootstrap paradox imagines a book handed back in time to its own author. Who wrote it? Where did it begin? These are not just riddles, they are tests of our understanding. They expose the fragility of our logic when time loops upon itself. Some theorists propose alternate timelines, parallel universes born from each divergence. Others say the universe would protect itself, never allowing such contradictions to form. And perhaps they're right. But even if time travel remains fantasy, the way time bends and bows is not. It is real, measurable, and deeply unsettling. It tells us that our lives are not ticking along some grand, cosmic metronome. We are each riding our own current, shaped by the hills and valleys of the cosmos. So next time you glance at the clock, consider this: its ticking is not universal. It is a local dialect of time, whispered to you by your place in the universe, in the grand, ever-unfolding story of reality. Time is not a line, it is a living, breathing thing, and we are all suspended in its flow, drifting not together, but apart, each on our own stream, carried by gravity, speed, and the great unfolding mystery of the cosmos. The ancient universe whispered secrets long before language gave them names. In its silence, patterns formed spirals, waves, collisions that echoed across the expanding void. And in that quiet, time continued to ripple outward, touched by forces more powerful than imagination. But the deeper we peer into the cosmos, the more we realize understanding time is not about clocks or calendars. It's about perception, and how the universe stitches past, present, and future into a single, ever-shifting tapestry. Let's descend now into a realm where time is not just a feature of the cosmos, but a lens through which reality itself takes shape. Consider consciousness the spark that lets us mark the passage of time. Without awareness, time becomes meaningless. A rock does not feel the dawn. A wave does not mourn the tide. Only minds like ours give time its rhythm. But what if our very perception of time is flawed, a mirage crafted by biology and bounded by memory? Neuroscientists have long marveled at how our brains carve time into segments. Moments feel longer or shorter based not on duration, but on emotion. A joyful hour with a friend feels fleeting. A minute in fear stretches to eternity. This elasticity is no accident. It is our brain's way of prioritizing experience. But what if the universe, too, experiences a kind of memory? A record of past states etched into its structure. Every particle's position, every echo of a photon, tells a story. The cosmos, in a sense, remembers. In physics, this concept appears as entropy, the tendency for systems to move from order to disorder. Entropy is why a shattered glass won't reassemble itself, why smoke doesn't return to a fire, why time has a direction. This direction, known as the arrow of time, flows inexorably forward, from low entropy to high. And yet, the laws of physics are time-symmetric. If you reverse the equations, they still make sense. So, why does reality insist on marching forward? The answer may lie in the Big Bang. At that first moment, the universe began in a state of incredibly low entropy, an almost impossibly smooth arrangement of energy and matter. From that cosmic seed, disorder bloomed, galaxies formed, stars ignited, and planets spun into existence. In this view, the arrow of time exists not because time itself is biased, but because the universe started with such astonishing order. Imagine a deck of cards perfectly arranged. The moment you shuffle, disorder increases. Each shuffle creates more possible outcomes, more randomness. That's entropy. And just like with the deck, the early universe was exquisitely ordered. Everything since has been a shuffle, and every shuffle drives the arrow of time. But entropy doesn't just explain why time moves forward. It hints at a cosmic memory embedded in matter. The universe isn't just expanding, it's recording. Each new arrangement of particles, each shift in energy, is a page in the story of existence. The past doesn't vanish, it becomes part of the structure of everything that follows. Perhaps that's why the past feels fixed, while the future remains fluid. Now, let us shift from the grand to the granular. Picture a single atom on a distant planet, caught in the orbit of a star we'll never see. Its electrons vibrate. Their probabilities spread across time and space. In quantum mechanics, these vibrations are governed by a mysterious interplay of chance and causality. At this scale, time is not smooth, it's jittery, probabilistic, as if stitched together from quantum fragments. Physicists describe this with the term quantum decoherence. As quantum systems interact with the environment, they lose their indeterminacy and settle into definite states. It's this process that allows the classical world, the one we experience, to emerge from the quantum fog. Time, in this sense, is a byproduct of decoherence. When particles lock into history, the flow of time becomes real. Without decoherence, there is no clear past or future, only a blur of possibilities. This raises profound questions. If decoherence gives birth to time, then time itself may not be fundamental. It may be emergent, something that arises when complexity reaches a certain threshold. In a world of pure quantum states, past and future are illusions. Only the wave function, the full description of all possible realities, exists. And yet, here we are, living, breathing, counting the seconds. So what is the bridge between quantum timelessness and our lived experience? Some theorists propose a model known as the block universe. In this view, past, present, and future all coexist in a four-dimensional structure. Time doesn't flow. It simply is. Each moment is a coordinate in space-time, fixed and eternal. We, like characters in a novel, experience the story page by page, though the entire book already exists. The block universe challenges everything we think we know about free will. If the future already exists, are we truly choosing our paths or merely uncovering them? It's an unsettling idea, one that reframes time as a landscape rather than a river. But perhaps unsettling ideas are necessary when trying to grasp something as elusive as time. Others counter with a model of the growing block universe. In this version, the past and present are real, but the future is not yet. Time grows like a tree, each moment adding to a trunk of cosmic history. This view preserves a sense of becoming, of unfolding, of potential. It aligns more closely with our intuition that the future is open, unwritten. Still others explore loop quantum gravity, a theoretical framework that suggests space-time itself is quantized, made of tiny loops woven into a spin network. If true, then time might be composed of discrete units, like frames in a film reel. Continuity would be an illusion, just as a movie appears smooth even though it's made of still images. This theory would mean that between each tick of the clock, there exists a gap, an invisible breath where nothing happens, yet everything prepares to happen. We are left with a mosaic of possibilities, time as memory, time as entropy, time as quantum emergence, time as a static block, time as a growing organism, time as a flickering illusion of discrete frames. Each model brings us closer to an understanding, but none fully captures the experience of being alive in time. And perhaps that's the point. Time is not just a dimension, it is the stage upon which meaning is born. Our memories give weight to the past. Our dreams infuse the future with significance. Our choices stitch the present with purpose. The more we learn about time's mechanics, the more we are drawn to its poetry. Because in the end, to understand time is to understand ourselves, not just as creatures who endure it, but as beings who shape it through thought, memory, and imagination. Time may be bent by gravity, slowed by speed, blurred by quantum uncertainty. But in every heartbeat, every tear, every laugh, we feel its passage, and that, more than any equation, is the deepest truth we know. The journey continues. In a universe where time stretches and curls like an ancient river winding through alien terrain, our attempts to understand it are like casting stones into water and watching the ripples collide. With each discovery, the surface shimmers anew, revealing depths we hadn't imagined. Now, we turn our gaze to the most enigmatic arenas where time behaves not only strangely, but perhaps incomprehensibly: black holes, cosmic strings, and the potential end of time itself. Black holes are not merely objects of immense gravity. They are gateways to extremes where space folds, light hesitates, and time itself grinds nearly to a halt. As you approach the event horizon, the boundary beyond which nothing escapes, the flow of time, slows to an imperceptible crawl. To an outside observer, an infalling object appears to freeze, forever suspended on the edge. Yet for the traveler, time remains normal until the final moment, a quiet descent into the unknown. This duality, where time appears frozen and flowing simultaneously, tears at the fabric of our understanding. Inside the event horizon, our equations break down. Space and time trade roles. The singularity, a point of infinite density, is not just a place but a moment in time where all paths end. What lies beyond is beyond our physics, perhaps beyond reason. But black holes may also be keys, not just tombs. Some theorists propose they harbor bridges, wormholes to distant parts of space and time. If such structures exist, they could allow shortcuts through the cosmos or even time travel, provided you survive the tidal forces. This is not science fiction. These solutions arise naturally in Einstein's equations. The question is not whether they can exist, but whether reality permits them. Parallel to this mystery are the threads of cosmic strings, hypothetical defects in spacetime that may have formed moments after the Big Bang. Infinitely long, yet unimaginably thin, they carry immense tension, warping spacetime in strange and beautiful ways. If two strings pass each other at high speed, they might create closed time-like curves, loops in time. In theory, such loops could allow travel into the past. Yet nature, as it often does, may conspire against such ambitions. The chronology protection conjecture, proposed by Stephen Hawking, suggests the universe prohibits time paradoxes by making such loops unstable. A kind of cosmic firewall might ignite whenever we try to twist time into a circle. Time, it seems, resists being rewritten. As we ponder the far reaches of time, we must also consider its fate. What becomes of time as the universe ages? Cosmologists speak of several endings: the Big Freeze, the Big Rip, the Big Crunch. Each paints a different future. Each reshapes time itself. In the Big Freeze, the universe expands forever, growing colder and emptier until no heat, no light, no activity remains. Time does not stop. It becomes irrelevant, with nothing changing, no events occurring. time loses its meaning. It's a death not of destruction, but of silence. In the Big Rip, the fabric of space expands faster and faster, eventually tearing apart galaxies, stars, planets, atoms. Even time itself may fragment. As distances stretch beyond limit, causality shatters, and the arrow of time dissolves into chaos. The Big Crunch imagines a universe reversing course, collapsing inward until all matter returns to a singular point. Time, running forward all the while, may halt or even reverse in this final contraction. Could we experience our lives in reverse, unraveling memory by memory, breath by breath? There is also the possibility that time is cyclical. Some cosmological models propose a rebirth, a new Big Bang, following the collapse. Time, like a phoenix, rises from its ashes. In such a looped cosmos, history might repeat. Are we living a life lived countless times before? Each scenario forces us to ask, does time have an end? And if so, what lies beyond it? If time is a property of our universe, then its end might be the end of everything we can possibly know. Or perhaps, beyond the final tick, lies something stranger, another realm where time, if it exists at all, wears a different face. Still, time's story is not all distant speculation. It plays out intimately in our daily lives. Every human culture has invented ways to market sundials, hourglasses, atomic clocks. We build calendars, celebrate anniversaries, grieve the passing of years. Our lives are narratives written in the ink of time. Even our bodies are timekeepers, the ticking of the heart, the cycling of cells, the arc of aging, all bound to time's flow. But we are more than passengers. We are architects of memory and anticipation, bending time within our minds. Through stories, we travel to the past. Through imagination, we visit futures that may never come. We give time color, meaning, emotion. Art, music, and literature stretch time, folding moments into eternity. A song can make 3 minutes feel infinite. A photograph freezes a heartbeat forever. Through expression, we resist time's erosion. We tell stories not to stop time, but to live alongside it, to make peace with its passing. And yet, even peace is not always easy. Time brings change, loss, endings, but it also brings healing, growth, renewal. The same current that erodes also nourishes. We build dreams on its flow. So as we journey further into the nature of time, we find not just science, but humanity. Not just equations, but experiences. Time is not merely a dimension of the universe, it is the theater in which our lives unfold. To understand it is to deepen our place within it. Now, let us wade deeper into the mystery, not through galaxies or quantum loops, but into the nature of time as it relates to identity, memory, and the boundless ocean of imagination. If the universe writes its story in the motion of stars, we write ours through the quiet flickers of thought. And in that inner cosmos, time flows differently. The human mind is a time machine, not made of gears or circuits, but of neurons and stories. We travel backward in memory, sometimes so vividly that the past feels present. We leap forward in imagination, projecting ourselves into futures we hope or fear. This temporal elasticity is not just poetic, it's a neurological truth. The brain does not merely record time, it reshapes it. Studies have shown that when we recall an event, the same areas of the brain that were active during the event reactivate. Memory is not playback, it is reliving. This means the past is not gone. It's reanimated each time we remember. In this way, time within us is cyclical, not linear. A grief from 10 years ago can bloom with fresh tears. A joy from childhood can return with aching clarity. Our inner timeline is a spiral. And yet, memory is fallible. It blends, distorts, invents. We often remember what we wish were true, or what we feared most. The brain edits without our permission, inserting emotional truths where factual ones falter. This is not a flaw, it's a feature. Our memories shape our sense of self. They are less about accuracy and more about meaning. In this light, time becomes not a ruler but a brush, each memory a stroke of identity, painting who we are. And because memory is mutable, so are we. We are not static beings traveling through time. We are fluid, formed anew each moment by the stories we choose to remember. But memory alone doesn't define our temporal experience. Consider anticipation, the emotional resonance of what has not yet occurred. Hope, dread, wonder. These are not tied to the now, but to what might be. Our minds reach forward just as often as they reach back. Time's power over us lies in this dual tension, remembrance and expectation. Religions and philosophies have long grappled with this. In many traditions, time is a path to transcendence. Eastern philosophies speak of cycles, samsara, rebirth, karma as endless loops where time is not escaped, but mastered, enlightenment. In some sense, is freedom from the illusion of time. In the West, time often flows toward a divine culmination, an end, a judgment, a resurrection. Both views imbue time with spiritual gravity. But not all visions of time are hopeful. Existentialists like Heidegger frame time as the shadow beneath meaning. To live authentically, he argued, is to confront the reality of our own finite time. Death gives urgency to choice and weight to freedom. Without time, we would have no stakes, no reason to act. In this view, every moment is sacred because it cannot be reclaimed. The Latin phrase memento mori, remember that you must die, is not a morbid warning, but a call to awaken. To be conscious of time is to honor it. Art captures this reverence. A film is a measured dance through time, each frame a decision, each cut a shift in tempo. Great directors bend time, stretching it in a lingering glance, collapsing it in a montage. They show us that time is not just experienced, but orchestrated. Poets, too, are time sculptors. A single line can contain centuries. A haiku can suspend a second in eternity. Through metaphor, rhythm, and silence, poetry makes time feel, not just pass. Even architecture plays with time. Ancient temples, eroded by wind and rain, remind us of how long a stone can remember. A crumbling facade tells of civilizations past. We walk through cities like layered texts, reading the stories etched in their walls. But what of the time we cannot feel the deep time of geology and cosmology, the span of billions of years over which mountains rise and erode? Stars form and collapse, species emerge and vanish. This time is humbling. It reminds us that our lifetimes are flickers, brief and bright. And yet, even these flickers leave traces. A child's laughter, a carved name, a whispered idea all ripple forward. In physics, these ripples may echo as gravitational waves, tiny distortions in space-time caused by massive events. But in human terms, they echo in culture, memory, legacy. Perhaps that is the true triumph of consciousness, to leave imprints in time. So, we dance in this tension between insignificance and importance, between knowing we are small and choosing to matter anyway. We measure time not just in seconds, but in stories, not just in change, but in meaning. And meaning, unlike time, can expand endlessly. The clock ticks, the stars wheel, and within each of us, a universe of time pulses quietly. Let us now come to the threshold where understanding turns into awe, where the pursuit of time's nature begins to reveal something even greater connection. For in all our attempts to dissect time, to measure and model it, what we are truly seeking is our place within it. Time is not merely a backdrop to our lives, it is the thread that stitches us to one another, to the past, to all that might come. We live in time, but we also live through each other. Every conversation, every kindness, every shared silence is an exchange of temporal essence. When you remember a loved one, you do not simply revisit an image you cross time, reach backward and bring them forward into now. In this way, memory becomes a form of communion, and storytelling becomes a time machine that binds people across generations. A child's lullaby may contain echoes of a song sung 1,000 years ago. A sacred text passed hand to hand can carry the breath of the ancients through language. We defy oblivion. But even more than memory, empathy is the miracle that bends time. To feel another's sorrow as if it were your own, to inhabit their moment that is a collapse of separation. It is time folded not by physics, but by compassion. And perhaps this ability to connect is humanity's most powerful defiance of entropy. We build cathedrals, libraries, cities not merely to endure, but to declare we were here, and we mattered. Our monuments may crumble, but the act of building is a statement against the erasure time brings, and though many voices are lost, each one carried forward changes the shape of the future. Consider the legacy of ideas. A thought, once spoken, once written, can ripple far beyond its moment. Newton's laws, Einstein's equations, a poet's verse, a scientist's vision, these do not remain locked in their own era. They radiate. They change the trajectories of lives yet unborn. The present, then, is never just a moment. It is an intersection, a collision of what has been and what could be. And at that intersection stands each of us, finite, yes, but capable of infinite resonance. When we speak of time, we are also speaking of loss. We lose people, places, eras, but we also gain. We inherit. We become. Time's passing is what makes beauty poignant and love enduring. The fragility of each moment is what makes it shine. Like a snowflake melting on a fingertip, its value is in its transience. This is the paradox we must hold. Time both takes and gives. It carves lines on our faces and wisdom into our hearts. It dissolves illusions, but reveals truths. It humbles us, but also empowers us to leave marks that outlast our days. So perhaps the true nature of time is not merely to measure, but to transform. To live in time is to evolve, to create, to heal, to remember, to hope. Time, then, is not the enemy. It is the canvas, and what we paint upon it, our acts of love, of courage, of imagination, those become the constellations by which others navigate. We began this journey at the birth of the universe, among the rippling fires of creation. We traveled through stars and theories, equations and paradoxes. We stood at the edge of black holes, walked the quantum foam, and traced the arc of aging across the soul. We have glimpsed how time bends, stretches, loops, and sings. But in the end, time's greatest mystery may be its invitation, not to solve it, but to live deeply within it. To notice the light in a stranger's eye, to savor the echo of laughter, to forgive and be changed, to love, and let that love ripple endlessly forward. Because while time moves on, meaning does not decay. Every true act resonates beyond its hour. So, as the seconds gather and the stars continue their silent dance, let us not ask what time is, but what we will do with the time we are given. The journey through time is the journey through ourselves. And though the river flows forward, our footprints, our voices, our dreams, these remain endlessly. Beneath a starlit sky, where the hush of night settles over the earth and each shimmering point of light trembles with ancient fire, one cannot help but wonder what lies beyond. Every star is not merely a distant sun, but a portal into the unfathomable, the grand celestial unknown where reality bends and mystery reigns. This is the threshold where questions take root. What is our place in the universe? Why does it behave in ways that defy our best theories? What secrets lie curled within its deepest shadows? The cosmos, silent and unyielding, challenges us not with violence but with enigma. From the earliest human skywatchers charting stars with bare eyes to today's theorists manipulating the language of quantum fields, we have always sought to pull back the curtain of the night. But the more we discover, the more the void seems to whisper. What if the anomalies we observe, those strange alignments, fading stars, and silent signals are not merely noise in the data, but the universe itself, speaking in riddles we have yet to learn how to read? To stand beneath the stars is to stand beneath a mystery that grows deeper the more we illuminate it. The universe, once thought to be a tidy, expanding field of matter and energy governed by elegant laws, now reveals itself to be full of quiet rebellions against order. Consider the light that has traveled for billions of years to reach us, its journey long and tireless, weaving through dust, gravity wells, and magnetic fields only to arrive as a whisper on the lens of our telescopes. In that whisper lie secrets, background noise that isn't noise, variations that shouldn't exist, alignments too precise to be dismissed. The cosmic microwave background, for instance, was once considered the ultimate proof of a smooth, isotropic universe born from a hot Big Bang. But even it holds a dissonant note, a peculiar alignment known ominously as the axis of evil, where temperature fluctuations in the CMB appear to line up along the plane of Earth's orbit, violating the assumption that the universe should look roughly the same in all directions. Is this a cosmic coincidence? A statistical quirk? Or something far more profound, a fracture in the symmetry of space-time itself? This anomaly, undeterred by new instruments and refined data, endures. It raises questions not just about the early moments of the cosmos, but about whether our position within it is as ordinary as we once believed. It challenges the cosmological principle, the idea that no place in the universe is special, but what if it is? Other anomalies compound the puzzle. The dipole repeller, a vast region of space with an apparent gravitational push, defies intuition. It is not an object, not a cluster of mass, but rather a void, a sprawling absence that reshapes the trajectories of galaxies, guiding their flow not with attraction, but repulsion. While the great attractor draws matter toward it with an invisible hand, the dipole repeller seems to sculpt galactic motion in the opposite direction, as though the universe itself breathes in and out across inconceivably large scales. What could give emptiness such force? The mere existence of such a repulsive influence suggests that gravity, our most familiar of cosmic forces, may behave in ways we do not fully understand when confronted with true emptiness. Or perhaps it is not gravity alone at play, but dark energy or some other force not yet woven into our equations. These vast structures or anti-structures mock our instincts about cause and effect, pull and push, presence and absence. They dance just beyond comprehension, shaping the destiny of galaxies as if by phantom touch. And there are trails, like fingerprints left behind after celestial collisions, ghostly streams of stars, stretched across the sky in delicate, fading arcs. Speak of ancient galactic mergers, tides of destruction and rebirth played out on unimaginable timescales. These galactic ghost streams are not merely beautiful, they are memory given form. They drift silently through the cosmos, so faint that even our best instruments strain to detect them. They are what remain after a smaller galaxy is swallowed by a larger one, its stars torn and scattered, leaving behind glowing trails like the long sigh of something once whole. The Sagittarius stream in our own Milky Way is a haunting example, a whisper of a past collision still echoing through our spiral arms. These structures offer history lessons, not written in books, but in gravity and light. They remind us that the cosmos is not static, not serene, but kinetic and violent beneath its tranquil veneer. Yet these same trails also blur the edges of our understanding. Some do not conform to our models of gravitational dynamics. They twist and stretch in ways that suggest forces unaccounted for, or events beyond the bounds of prediction. They force us to look not just outward, but backward, trying to piece together a puzzle scattered across billions of years and billions of stars. Even the brightest lighthouses of the cosmos seem to conspire in mystery. Quasars, brilliant, ancient engines of energy surrounding supermassive black holes, are not merely distant beacons. They carry hidden messages in their light. Their radiation, when filtered through our instruments, shows signs of polarization, waves of light aligning in directions that, across billions of light years, should be random, yet they are not. Patterns have emerged, alignments stretching across vast swaths of sky, as if entire constellations of quasars had somehow synchronized their polarizations. What could cause such coherence across such distance? Some theorize that intergalactic magnetic fields have bent their light over time, imprinting an unseen structure onto the cosmos itself. Others suggest that these alignments are fossils' imprints of primordial conditions, frozen into the scaffolding of the universe at the moment of its birth. Or perhaps they hint at something even more radical, that space-time, on the largest scales, is woven with hidden symmetries, echoing patterns that transcend galaxies, epochs, and comprehension. Here again, we are left with signals we can observe, but not fully explain a Morse code tapped out by the stars that we have only just begun to translate. Even closer to home, the solar system harbors its own enigmas. Beyond Neptune lies the Kuiper Belt, a frozen hinterland of icy remnants from the solar system's formation. It should, by all accounts, stretch smoothly outward into the void, gradually thinning, yet at a distance of about 50 astronomical units. The distribution of objects drops off sharply a cliff in space known simply as the Kuiper Cliff. Why, what truncates the solar system so precisely? Could it be the gravitational influence of a hidden planet, an as yet unseen Planet 9 lurking in the cold, dark beyond, or is it a relic of the solar system's chaotic infancy, shaped by migrations of the gas giants and scattering collisions that cleared the outskirts like broomstrokes in dust, whatever the cause? This cutoff speaks of an invisible boundary, a line the universe itself seems to have drawn at the edge of our planetary domain. It is both a limit and a dare, calling us to cross it and find what lies on the other side. Far stranger still are the voices from the deep. Fast radio bursts, blindingly quick flashes of radio energy have confounded astronomers since their discovery. Some last only milliseconds, yet carry as much energy as the sun emits in days. Many come from distant galaxies, their origins veiled, their mechanisms unknown. Some repeat, some do not. A few have been traced to magnetars highly magnetized neutron stars whose fields are so strong they can twist atoms and erase data from spacecraft from thousands of miles away. These cosmic monsters, born in the death throes of giant stars, are engines of energy and chaos. Their quakes can ripple space-time. Their emissions reach across the stars. And yet their numbers are so few, only dozens known, that each new discovery reshapes our understanding of stellar death and high-energy physics. Could they be the source of these eerie bursts? Or do we still lack the key to understanding these signals, which seem to come from everywhere and nowhere, whispering a message we can hear but not yet decipher? And then there are the silences, the empty spaces that speak louder than noise, intergalactic voids, cosmic deserts where galaxies thin and then vanish, where gravity goes quiet and the light dims. Some of these voids are so vast that entire superclusters could drift through them without ever meeting another galaxy. Yet they are not nothing. They hold dark energy, magnetic fields, perhaps even unknown particles. Signals have been detected from within these voids, strange, persistent radio waves from regions where no galaxies dwell. Could these be echoes of ancient collisions, the death cries of long-vanished structures, or something entirely other? Phenomena born in isolation, beyond the reach of our frameworks. The universe does not offer us clean conclusions. It offers us riddles, wrapped in starlight, pulsing through the radio dark, folded into patterns of gravity and electromagnetic hush, for all our equations and models, for all our machines perched on mountains or circling Earth in the cold void. We remain in the infancy of cosmic comprehension. These anomalies, these strange behaviors and misbehaving lights, do not close the book of science. They open it. They remind us that the universe is not only grand, but layered with meanings we do not yet possess the language to describe. In every unexplained alignment, every vanished star, every echo from nowhere, we hear it again, the whisper in the darkness that says, "Keep going. There is more. There is always more." And in that whisper, fragile and fleeting, is the truest music of the cosmos, not silence, not certainty, but wonder. Cosmic alignments and recoiling voids. Imagine drifting through the void, beyond the veil of stars, where silence reigns and the laws we once thought immutable begin to tremble. Out there, far from the warmth of the familiar, the universe whispers not in words, but in alignments, patterns, and movements subtle, defiant signatures that unsettle the very foundation of our cosmic understanding. This part of our journey ventures into a realm of disquieting mystery, where two anomalies rise not with thunder, but with an eerie, quiet defiance, the axis of evil and the dipole repeller. These are not characters of myth, but signatures etched into the cosmic canvas, challenges to the assumptions that have guided generations of cosmologists. They speak to us from the deepest stretches of space, not with clarity, but with riddles that make us question whether the universe we inhabit is as random and isotropic as we once believed, or if some vast and hidden architecture awaits discovery just beyond the limits of our perception. As we peer into the relic radiation of the Big Bang and trace the silent flows of galaxies, we begin to see something uncanny, alignments that should not exist, and empty places that push the cosmos itself. In this search for meaning, the line between science and wonder begins to blur, as we confront the unnerving possibility that there may be forces and forms at work that remain cloaked, not only in distance, but in a silence deeper than space. It begins with light, not the ordinary kind that flits through windows or reflects off water, but the most ancient glow, the afterimage of creation itself, The cosmic microwave background, or CMB, is our universe's baby picture, a relic radiation imprinted on the fabric of space some 3,000 years after the Big Bang. It is faint, cold, and nearly uniform, a soft hiss of microwaves whispering from all directions, a cosmic lullaby that lulled astronomers into thinking the universe was well-behaved on large scales. The cosmological principle, the idea that the universe, averaged over vast distances, looks the same in every direction, was long held as a guiding assumption, a bedrock of cosmology. But then came the anomaly, an unsettling smudge in the data, a pattern that refused to fade. First detected by the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite, a curious alignment appeared in the CMB's temperature fluctuations, stretching across the sky along a particular axis. This unlikely alignment, statistically improbable and persistently present, soon earned a provocative name: the axis of evil. Its moniker, coined half in jest, captured the discomfort it stirred among scientists. Here was something that shouldn't be: a crack in the elegant symmetry of the cosmos. The axis aligned suspiciously with the plane of Earth's orbit, an alignment that raised the possibility of measurement bias or local contamination. Yet attempts to scrub it away through modeling and corrections only seemed to confirm its tenacity. Like a shadow that won't dissolve in the light, the axis lingered, suggesting a directional preference in the oldest light. We have an affront to isotropy, and perhaps to simplicity itself. The axis of evil confronts us with more than just a glitch. It threatens the philosophical underpinnings of cosmology. If the universe has a preferred direction, if the oldest photons we can see are etched with asymmetry, then the very idea of a uniform cosmos falters. Theories abound to explain it. Some posit that the anomaly is an observational artifact, a statistical fluke born from our single vantage point within a vast multiverse. Others propose that we're glimpsing the aftershock of something immense, perhaps a collision with another universe, one that grazed our own like a ghost ship scraping the hull of reality. More speculative still are hypotheses involving primordial magnetic fields or unknown forms of anisotropic dark energy that might have imposed structure on the infant universe. In each case, the axis of evil invites not comfort, but vertigo, a sense that we are standing on the edge of an unfinished story, whose ending we are not yet meant to read. And yet, for all its menace, it also ignites the flame of curiosity. What if this anomaly is not a problem, but a clue? What if it is not an error to be corrected, but a signal, however faint, that we are glimpsing the deep scaffolding of the cosmos, a design far stranger and more deliberate than we have ever dared imagine? As our gaze shifts from the relic light of the early universe to the present dance of galaxies, we encounter a second anomaly, equally silent and equally defiant. The dipole repeller is not a glowing beacon or a gravitational anchor. It is an absence, a void with invisible hands, unlike the axis of evil, which unsettles the heavens with its alignment. The dipole repeller exerts its mystery through motion, galactic motion. In the cosmic sea, galaxies are not stationary islands. They flow, pulled and pushed by the uneven distribution of mass. For decades, astronomers noticed that our local group of galaxies was moving at an unusually high velocity relative to the CMB, pulled in part by a massive concentration of galaxies known as the Great Attractor. But this pull was not the whole story. The trajectory of motion required something more, an unseen push. In 2017, astronomers analyzing the Cosmic Flows 3 survey discovered that our motion was not only due to gravitational attraction, but also to repulsion. They identified a vast, underdense region of space, a void with enough gravitational contrast to repel galaxies. This ghostly absence became known as the dipole repeller. Unlike the great attractor, the dipole repeller cannot be seen in traditional images of the sky. It is a structure of inference, known not by what it emits, but by how it shapes the flows around it. Galaxies flee from its coordinates, their motions echoing the contours of gravitational imbalance. It is, in essence, a negative space whose influence rivals that of the densest clusters. And therein lies the paradox. How can emptiness exert a force? The answer lies in the subtleties of gravity on cosmological scales. Dense regions pull, but voids, being less dense than their surroundings, create gradients that effectively push. It is not a repulsion in the electromagnetic sense, but a gravitational choreography, a recoiling dance that emerges from contrast. The dipole repeller is a sculptor of galactic paths, a silent architect shaping the universe not through presence, but through absence, and like the axis of evil, it raises profound questions about the structure and origin of cosmic flows. Are these alignments and motions mere accidents, or are they echoes of deeper laws, hidden dimensions, or a history we have yet to uncover? Together, the axis of evil and the dipole repeller frame a haunting question. What if the universe is not isotropic, not homogeneous, but instead patterned by unseen forces and fossil scars of primordial events? What if voids and alignments are not quirks but keys? Keys that unlock doors to a pre-inflationary universe, to entanglements between our cosmos and others, to a topography of space shaped not only by mass and energy, but by conditions we cannot yet measure. In these questions lies the emotional weight of cosmology, the tension between what we observe and what we believe. These anomalies do not merely tweak equations, and they invite a reimagining of the universe as a place not of serene uniformity, but of dynamic asymmetry, of hidden engines that propel galaxies and stretch the very fabric of space. It is humbling to consider that our most powerful tools, satellites, surveys, simulations, still illuminate only fragments of the grand design. Each new map of the sky is like a lantern in a cathedral, revealing frescoes too vast to grasp, too dim to decipher in full. And yet we are driven onward, not because we expect closure, but because each anomaly is a promise that the universe still has stories to tell. The axis of evil and the dipole repeller are whispers from the edge of comprehension, subtle deflections in the script of space and time. They are reminders that reality is not always polite, not always symmetric, not always predictable, but it is beautiful, melancholically beautiful, because to witness the universe in its mystery is to be part of something that endlessly outpaces us, that invites us to reach, even when we cannot grasp. The great irony is that these vast structures, the axis stretching across the sky, the repeller lurking in the abyss, are discovered not with our eyes, but with patience, mathematics, and an unyielding faith that patterns, however faint, can be found. And so we search, measuring polarization angles, mapping redshifts, constructing gravitational velocity fields like cartographers of an unseen continent. In this work, cosmology becomes more than science. It becomes a kind of pilgrimage, a journey toward the hidden harmonies of the universe. Perhaps one day, with more precise instruments and deeper theories, we will see not just the shadows, but the causes behind them. Perhaps we will trace the axis to a bubble wall in a multiverse sea, or understand the repeller as a relic of topological variations seated in a pre-quantum epoch. Or perhaps we will find only deeper puzzles, each answer birthing a new mystery in an infinite regress that mimics the very expansion of space. But even then, we will not have failed, for the goal is not to end the mystery, but to expand the horizon of the known. These anomalies, these trembling irregularities in the fabric of the cosmos, are not cracks in science, they are its frontier. They call us forward, into the deep, into the cold, into the silence where stars align and voids breathe. And in that silence, we listen. We listen for the shape of what is still to come. Echoes of galactic memory, streams and light patterns. Imagine drifting in the silence between galaxies, where time slows and ancient light whispers across the dark. In this inky canvas, there exist traces so faint they nearly escape the eye. Tenuous, gossamer trails stretched across millions of light years like the fading footprints of celestial giants. These are the galactic ghost streams, ethereal remnants of ancient galactic collisions, the long-forgotten relics of cosmic cannibalism and gravitational entanglement. They do not blaze across the cosmos like quasars or erupt in cataclysm like supernovae. Instead, they linger, delicate and spectral, formed when galaxies brush too close, ensnared by each other's gravity in a silent, slow-motion dance that ends with one devouring the other, as stars are stripped from their hosts and slung into the void. They form ribbons of stellar debris, haunting monuments to mergers that took place eons ago. These streams are like faint murmurs of memory, barely perceptible against the glow of the galactic night. And yet they hold stories of breathtaking violence and transformation to the naked eye. They are invisible to astronomers with deep sky surveys and wide-field infrared telescopes. They are fragile stitches in the cosmic fabric, hinting at episodes of upheaval that reshape the architecture of entire galaxies. Among them, the Sagittarius stream in our own Milky Way stands out, a sprawling loop of stars torn from a dwarf galaxy as it was gradually consumed by our galactic core. Like a ghost circling its grave, it arcs across the night, testifying to a time when our galaxy was not a quiet spiral, but a predator in a stellar jungle. Detecting such streams demands more than technology. It requires patience, serendipity, and a relentless willingness to chase shadows. The stars within these streams do not burn brighter than their neighbors. They do not cry out. Their arrangement is their only clue, elongated, curved, whispering of orbits stretched by tidal forces, of gravitational embraces that reached across space and time. Long exposures, motion tracking, and digital sky surveys piece together these faint threads, revealing more of them with each passing year. And what they tell us is astonishing. The universe is not a static mosaic, but a dynamic, ever-evolving structure. Galaxies grow not just by birthing new stars, but by consuming one another, merging and assimilating in processes that take billions of years yet leave behind unmistakable scars. These ghost streams are fossils, and astronomers have become their paleontologists, reconstructing the family trees of galaxies from their long-lost limbs. Sometimes, the cannibal is not even the predator. Dwarf galaxies swept into larger hosts may themselves have devoured smaller companions in their own pasts. Each stream becomes a layered story, a branching history of creation and consumption. But not all cosmic memories are drawn in stars. Some are encoded in light itself, etched into the oscillations of electromagnetic waves traveling across unimaginable distances. Enter the quasar, among the most powerful and luminous objects in the universe. At the center of distant galaxies, supermassive black holes feast on infalling matter, releasing torrents of energy as they spin and blaze with the light of unmaking. These quasars are beacons from the early universe, some shining across the abyss for more than 10 billion years, yet their brilliance is not their only wonder. As their light journeys toward us, it becomes subtly polarized, its waves aligned in particular directions. Normally, light vibrates in every plane perpendicular to its path. chaotic and free. But when it interacts with magnetic fields, gas clouds, or dust, it becomes ordered, filtered. What's astonishing is that quasar light across billions of light years appears not only polarized, but aligned in ways that defy explanation. These polarization vectors, separated by cosmic gulfs that should render them independent, seem to point in similar directions, as if the universe itself is organizing the orientation of light. This phenomenon, so statistically improbable it borders on the uncanny, suggests that something deeper is at work, something embedded not in the quasars themselves, but in the intergalactic medium, in the very geometry of space-time, or perhaps in a primordial memory etched into the universe's infancy. What could cause such coherence on such enormous scales? Magnetic fields stretching across intergalactic space might subtly twist the light as it passes through, like ancient weavers guiding cosmic threads through invisible looms. These fields, though weak, can impose directionality over eons and distances, shaping the quasar's light into subtle patterns. Alternatively, the light may be passing through cosmic filaments, massive tendrils of dark matter and gas that form the scaffolding of the cosmic web. These structures could act as vast, anisotropic lenses, rotating and aligning light as it threads through them. Or perhaps we are seeing something even more profound, a fossil of the universe's initial conditions, a leftover ripple from inflation, frozen into the polarization of photons born in an earlier epoch. That these alignments might reflect some deep asymmetry in the fabric of the cosmos calls into question our assumptions about its isotropy, that it is the same in all directions. If this uniformity breaks, even in the subtlest ways, then our models must be revised, and the map of the universe redrawn. Quasar polarization may sound like a technical footnote, but it strikes at the heart of cosmology. These beacons, scattered across the cosmos, become a new kind of telescope, a way to look not at things, but through them, into the forces and fields that structure the universe. And yet, like the ghost streams, they are elusive, their light is faint, their signals buried in the noise of the cosmos. Detecting and measuring polarization with accuracy requires specialized instruments. Polarimeters capable of measuring the angle and degree of alignment with extraordinary precision. Observations must account for intervening dust, galactic emissions, and the vagaries of atmosphere and telescope. And yet, when these barriers are overcome, the patterns persist. Alignments emerge not in isolated regions, but across hemispheres, across epochs. The message, if there is one, is subtle but persistent. Something is shaping the light from the edges of the observable universe, something coherent, something large, something unknown. Together, ghost streams and quasar polarization form a kind of cosmic symphony, two very different melodies, each echoing across time and space, each whispering of hidden histories. One tells of gravitational violence and mergers past, the other hints at a lattice of invisible forces that shape light itself. They are not random curiosities, but pieces of a puzzle, suggestions that the universe contains an architecture we have barely begun to grasp. Perhaps there are relic symmetries from a time before stars, before galaxies, signatures from a deeper layer of physics that ripple upward into the structures we now observe. Perhaps these patterns reflect a universe that is not just expanding, but evolving toward complexity, toward coherence, toward something intelligible. Or perhaps they are signs of our own limitations, our anthropic perspective peeking through the veil, imposing order where there is only chaos. And yet, the data remains. The stars are there, the light is aligned, and the streams persist, drifting slowly like the last breath of something long gone. In this interplay of gravity and light, in the faint scars and luminous alignments, we glimpse a kind of galactic memory, a memory not made of neurons or thoughts, but of trajectories, distortions, and waveforms of the gravitational scripts galaxies follow, and the radiant signatures left in their wake. These memories are not conscious, but they are legible. They are inscribed across billions of light years, carried by stars and photons alike, waiting for minds patient enough to decode them. The cosmos, it seems, remembers not in stories, but in structure, not in words, but in wavelengths, and in that remembrance, we find both wonder and humility, for we, too, are part of this great memory. We are stardust reorganized into sentience, fleetingly aware of the ancient forces that shaped us. We look up, and in the light from distant quasars, in the wisps of ghostly star streams, we recognize something familiar, an echo of becoming, a fragment of a larger tale. And perhaps that is the greatest mystery of all, that the universe, vast and ancient and indifferent, speaks in patterns, and that we, ephemeral as we are, can still learn to listen. Perimeters of the known, the Kuiper Cliff, and the Magnetar Enigma. At the edge of everything we know, where the warmth of the sun fades into a pale glimmer and solar winds no longer blow with strength, there exists a silence that speaks of unresolved riddles beyond Neptune's orbit, where the Kuiper Belt sprawls like a frozen debris field circling the sun. Astronomers once expected a steady population of icy remnants fossils from the solar system's formation to stretch far into the darkness. Yet, just past 50 astronomical units, something inexplicable occurs. The Kuiper Belt abruptly ends. This stark drop in the number of objects, now hauntingly known as the Kuiper Cliff, is not a gentle fading away, but a sudden plunge. As if the cosmos changed its mind, no clear gradient, no slow diminishment, only a conspicuous emptiness where once there was anticipated abundance. It is a cosmic cliff edge where possibility falls into silence. What could have swept this region clean, or never allowed it to form at all? Some suggest the gravity of a distant, undiscovered planet, Planet 9, lurking far beyond our telescopic reach, pulling on icy bodies and warping their orbits into hidden pathways. Others propose that early migrations of Jupiter and Saturn, or ancient interactions with rogue stars, sent gravitational shock waves through the solar nursery, scattering debris like leaves in a storm. Still others argue that this edge is simply where the primordial protoplanetary disk faded into nothing, a natural outer boundary of the sun's original birth cloud. But none of these theories fully satisfy the abruptness, the precision, the mystery of the cliff. It remains an open question in planetary science, a glaring omission in an otherwise elegant model. This outer boundary is not just spatial, it is epistemological. The Kuiper Cliff defines not only a limit to where most trans-Neptunian objects dwell, but also to how far our current understanding can stretch before it falters. Spacecraft like Voyager and New Horizons have slipped into this realm, sending back ghostly portraits of icy dwarfs and lonely rocks, hinting at a frontier that remains largely unexplored. Here, our maps become probabilistic, our models wobble. The expected fades into the enigmatic. We are reminded that the solar system, for all our charts and probes, still keeps secrets in its outermost shadows. It is at these margins that our theories reveal their gaps, and we encounter the humbling truth that we are still, in so many ways, beginners. The Kuiper Cliff is not a final line, but an invitation, a question mark drawn in the cold, urging us to peer deeper, to search with sharper instruments, and to rethink the assumptions we have taken for granted. It is a gentle mystery, quiet in its challenge, yet profound in implication. If our solar system has such abrupt structural features we have yet to explain, what of other star systems? What of the galactic edge? What unseen forces shape the perimeters of the known? But as we contemplate the icy silence of the outer solar system, a radically different anomaly roars from across the void, an explosion of force and mystery found not in the cold, but in the crucible of stellar death, deep in the galactic graveyards. Among the remnants of supernovae dwell the magnetar's neutron stars with magnetic fields so intense they make even the strongest laboratory magnets seem like toys. These compact cores, only a dozen kilometers wide, yet holding more mass than our Sun, are the densest forms of matter known outside black holes. But some neutron stars go even further. A rare few evolve into magnetars, their magnetic fields 1,000 times stronger than typical neutron stars, reaching intensities that defy comprehension enough to warp atoms, crack open the crust of the star itself, and potentially rip the very fabric of space-time. These celestial monsters do not whisper their presence. They shriek, with sudden gamma-ray flares and bursts of high-energy X-rays. They unleash tantrums so powerful they can be detected across galaxies. In 2004, a magnetar in our Milky Way SGR 180620 emitted a flare so intense it briefly altered Earth's ionosphere. Despite being 50 light-years away, had it been closer, it might have fried our satellites or even our atmosphere. These eruptions are believed to stem from starquakes, sudden rearrangements in the crust of the neutron star. Driven by the immense stress of magnetic pressure, it is as if the magnetar itself struggles under the weight of its own internal chaos. But magnetars are not merely loud, they are elusive. Their lives are short, their births rare, and what they might be telling us could extend far beyond neutron star physics. In recent years, a tantalizing connection has emerged between magnetars and fast radio bursts, FRBs, brief, millisecond flashes of radio energy from distant galaxies that once defied all classification. The mysterious nature of FRBs, some repeating, others not, had fueled wild speculation alien technology, decaying cosmic strings, echoes of black hole mergers. Then, in 2020, an FRB was traced to a known galactic magnetar, suggesting a concrete astrophysical source for at least some of these phenomena. Yet even this apparent clarity deepens the enigma. How can such short, sharp signals arise from something so massive, so dense, so slow by comparison? What does it mean that magnetars can produce both high-energy gamma flares and low-energy radio flashes? Are we witnessing different facets of a single physical process? Or is the magnetar merely a conduit for more exotic mechanisms, perhaps involving quantum electrodynamics, axion-like particles, or interactions with the dark sector? Indeed, magnetars push the boundaries of our physical theories into regimes we cannot replicate on Earth. The magnetic field strength near a magnetar exceeds the quantum critical limit, where even the vacuum becomes nonlinear, altering the behavior of light and matter in ways predicted only by quantum electrodynamics. At these field intensities, atoms deform into pencil-thin structures, and photons can split or merge in defiance of classical expectations. Some theorists posit that magnetars might be natural laboratories for new physics, offering glimpses into the behavior of matter at the intersection of general relativity, quantum mechanics, and extreme conditions. Others speculate that these stars might help probe the elusive nature of dark matter, acting as gravitational traps for exotic particles whose annihilations might subtly alter magnetar dynamics. We are far from understanding them fully. Like the Kuiper Cliff, magnetars represent a kind of frontier, a place where our models hesitate, where equations strain, where intuition fails, They are not the edge of space, but the edge of physical law. The contrast between the Kuiper Cliff and the Magnetar Enigma is striking. One is quiet, remote, spatially mysterious. The other violent, compact, temporally sudden, and yet they share something fundamental. Both sit at the boundary of our comprehension. One is a puzzle of absence, the other of excess. One challenges our understanding of gravitational dynamics in the outskirts of our solar neighborhood. The other tests our knowledge of matter and magnetism at nuclear densities. One pulls us outward, the other inward, and both whisper, in their own dialects, of a universe richer, stranger, and more dynamic than we dared imagine. They remind us that reality does not conform neatly to human expectation. They force us to question our frameworks, not to discard them, but to evolve them, to stretch them toward truths we have not yet glimpsed. These phenomena, though distant, reflect something deeply human. We, too, stand at a kind of boundary between knowledge and mystery, between comfort and curiosity, just as the Kuiper Cliff marks the outer limit of what we thought we understood about the solar system, and just as magnetars push the internal coherence of matter to breaking. So we live in a state of perpetual inquiry, straining toward insight with instruments and equations, but also with wonder and metaphor. The universe does not give up its secrets easily, and yet, through cliffs and flares, through silence and fury, it speaks to us still. In that speaking, we are reminded that science is not merely the accumulation of facts, but the cultivation of awe, that physics, at its most honest, is an act of listening, and that even in the perimeters of the known, there are echoes of something vast and unnamed, waiting to be felt. Hidden cores and missing elements. In the frigid twilight of the solar system, far beyond the rocky inner planets and the familiar gas giants, drifts a world that whispers secrets it refuses to yield. Uranus, a cyan orb suspended in the void, is often overlooked, quiet, cold, seemingly uneventful, yet beneath its serene surface lies one of the most profound enigmas of planetary science. Unlike Jupiter or Saturn, with their storms and swirling belts, or even Neptune, its deep blue twin, Uranus is eerily muted. It radiates almost no internal heat. Its thermal signature is so faint that the planet appears to emit less energy than it receives from the Sun, a stark contrast to its planetary siblings. This thermal silence suggests an interior unlike anything we've modeled, a core that may hold secrets not just about Uranus itself, but about the broader processes that shape the architecture of the solar system. And then, there is the tilt Uranus spins nearly sideways, its rotational axis lying almost in the plane of its orbit, like a planet tipped and forgotten. The cause may have been cataclysmic, a titanic collision in the solar system's youth, or the slow gravitational sabotage of unseen forces, sculpting its orientation over eons. This orientation has consequences: extreme seasonal cycles, a magnetic field misaligned from its core, and an interior structure that may be layered, chaotic, or fundamentally different from what we expect. We cannot peer directly inside. But we suspect that the core may be home to materials we barely understand, such as superionic ice, a state where water behaves as both solid and liquid, its ions moving like ghostly currents through a crystalline lattice. This strange form of matter, predicted in high-pressure simulations, may not only exist in Uranus, but dominate its internal structure. If so, it challenges how we model conductivity, heat flow, and the very definitions of phase transitions under planetary conditions. And in this planetary riddle, this elegant silence of Uranus, we find a metaphor for a deeper mystery, one etched not in planetary behavior, but in elemental fingerprints cast across the entire cosmos, for scattered throughout the stars, in the hearts of galaxies and the halos of ancient stellar remnants, lies a mismatch that has troubled cosmologists for decades: the lithium problem. When the universe was but minutes old, it forged the first elements in a process known as Big Bang nucleosynthesis hydrogen, helium, and traces of lithium. The ratios of these elements were predicted with extraordinary precision, a rare success in cosmology's attempt to align theory with observation. And yet, as we look to the oldest stars, those ancient population tube beacons whose light carries the memory of primordial creation, we find far less lithium than we should. In some stars, the lithium abundance is a third of the expected value. In others, it's nearly absent. This is no small discrepancy. It's a fracture at the base of a model we otherwise trust. A problem that refuses to be soothed by statistical error or observational imprecision. The elements are the universe's memory. When one of them goes missing, it's as if part of our cosmic history has been redacted. So where is it? Some theories suggest that lithium is not truly missing, but hidden, burned away in the interiors of stars through mechanisms more subtle than we've accounted for. Perhaps convective mixing or atomic diffusion pulls lithium deep into stellar hearts, where it is destroyed in nuclear reactions and never reemerges. But this hypothesis struggles with uniformity. Why do so many stars, across such varied types and epochs, show the same unexpected shortfall? Could there be flaws in our nuclear physics, in the reaction rates assumed during Big Bang nucleosynthesis? Or are more exotic culprits at play? Some physicists have pointed fingers at hypothetical particles, axions, sterile neutrinos, or other dark sector interactions that might have altered the cooling rate of the early universe or shifted the balance of elemental synthesis. Others have speculated on asymmetric baryogenesis, time-varying constants, or alternative cosmologies that tweak the fundamental timeline of the early universe, just enough to explain the discrepancy. These are not fringe ideas, but serious conjectures emerging from the space between theory and observation. From the tension that arises when a model elegant in its mathematics confronts a sky that refuses to conform. The lithium problem and Uranus's interior, seemingly unrelated, are bound by a deeper truth. They are reminders that science, for all its rigor, remains a human endeavor, fallible, fragile, always incomplete. Each model we build is a map, not the territory, a sketch drawn with the best instruments we possess, guided by the logic of mathematics and the humility of measurement. But some landscapes resist our gaze. Some truths remain just out of reach, like the icy pressure chambers deep inside Uranus, or the primordial reactions that lit the first fires of elemental birth. In both cases, we are left navigating by inference, reaching for understanding in the darkness between data points. And yet, it is in that reaching in, that stretching of theory toward anomaly, that science becomes most profound. It is not in certainty, but in doubt that discovery lives. To contemplate these mysteries is to confront a universe not built for our comprehension, but rich enough to reward our persistence. Uranus drifts in its orbital solitude, bearing scars of trauma and containing an interior that may hold new states of matter. Lithium whispers of a misremembered beginning, its absence questioning our confidence in the earliest pages of the cosmic story. Together, they speak of a cosmos where every silence is significant, every inconsistency a clue. We do not know if we will solve these puzzles in this century, or ever. Perhaps new missions to Uranus will finally dive into its atmosphere and pierce the veil of its interior. Perhaps future telescopes will refine our stellar models, or uncover new particles that restore lithium to its rightful place. Or perhaps, as often happens in science, the answer will come from an unexpected angle, a theoretical leap that reframes the question itself. Until then, we carry these anomalies like riddles folded into the star maps of our understanding. We look outward with eyes that seek symmetry, but find beauty even in asymmetry. We listen for the rhythm of reason, but are not afraid of dissonance, because somewhere in that dissonance lies the voice of the cosmos, still speaking, still singing, still waiting to be heard. Radio ghosts and dust veils, signals from the unknown, in the boundless dark between galaxies, where the thin fabric of space stretches in silence and the density of matter thins to near nothingness. There come flickers, faint, defiant flickers, not of light, not of structure, but of radio waves, ghostly whispers traveling unimaginable distances, haunting the cosmos with their slow, drifting rhythm. These are not the familiar crackles of pulsars or the burst patterns of known stars. They are slower, broader, stranger. They rise not from within the spiraling arms of galaxies, but from the peripheries of cosmic maps, from voids that should be silent. For decades, astronomers have cataloged strange radio emissions that seem to come from nowhere, flickering into the sensitive ears of radio telescopes with no matching optical source. Some drift in frequency, others persist without explanation, and a few arrive with such regularity that speculation drifts from the scientific to the speculative, from the realm of plasma and black holes to the eerie corridors of hypothetical technology and unknown cosmic actors. And yet, to leap to aliens is to skip the poetry of the question. What if these signals are the language of galaxies, speaking in tones we have only begun to understand? What if this radio static is the soundtrack of the void, a resonance of collisions, of magnetized plasma arcs, of dark matter interactions far beyond our current physics? Among the leading contenders for these ghost signals are active galactic nuclei, supermassive black holes at the centers of galaxies, cloaked in magnetic fury, that can send out collimated jets of energy stretching across millions of light years. These radio lobes, interacting with the intergalactic medium, can distort and scatter, creating echoes that outlive their source. Or perhaps the sources are dying stars in intergalactic exile, ejected from their galaxies by gravitational chaos, now pulsing their last messages across a vacuum no one was meant to hear. Some signals may even originate in galaxy cluster interactions when massive galactic bodies merge. The resulting plasma shocks can emit radio waves on scales that defy intuition. And yet, the true mystery lies in the ones that do not fit any known category. They do not repeat like pulsars. They do not flash like fast radio bursts. They drift, they linger, and then they vanish. They do not ask to be found. They simply exist, waiting to be noticed. And what of the veils? If radio signals are the voices of the void, then interstellar and intergalactic dust clouds are its silences. These clouds, composed of microscopic grains of carbon, silicates, and frozen gases, stretch across the Milky Way and beyond, scattering and absorbing light in ways that both reveal and deceive. They are born in the atmospheres of dying stars and the shock waves of supernovae, but they do not die quickly. Instead, they drift carried by the tides of galactic winds and magnetic fields, accumulating in dark filaments that stretch across the sky. To the naked eye, they are nothing, but to astronomers, they are distortions biasing the light from distant galaxies, muting the brightness of supernovae, reddening the colors of starlight. In the pursuit of precision cosmology, dust is the eternal contaminant, but it is also a storyteller. For inside those grains are chemical records of ancient furnaces, isotopic signatures of stellar deaths, and the raw material of future planetary systems. Dust is not just a nuisance, it is memory. It is the medium through which stars form and through which the light of the universe must pass. There are clouds vast and faint that defy classification. Cold, dark molecular clouds in the outer reaches of our galaxy harbor the seeds of future stars, yet others, high above the galactic plane, are so faint that they can only be seen when backlit by quasars or mapped by the dimmest of infrared echoes. These are the whispering veils of the universe, half visible, half imagined. Are they leftovers refused from galactic collisions, cast into the void like the spray of an ocean wave? Or are they the embryos of something new, nurseries not yet ignited, clumps of potential awaiting the right trigger? The answer remains as unclear as the clouds themselves. In every observation lies a distortion, in every correction, a new uncertainty, and still, we measure, we map, we model, we chase clarity through veils that shimmer and shift. It is humbling to know that some of the universe's greatest mysteries may not lie in what is distant or rare, but in what is faint, not in the spectacular bursts of gamma rays or the luminous death of stars, but in the slow pulse of radiostatic and the quiet glow of dust. These are the universe's margins, the things too dim to dominate, too subtle to ignore. They teach us that not all knowledge is bright, not all truths are loud. That in the quiet, in the veil, in the flicker, there is revelation, and in the search for meaning among the softest signals and the faintest shadows, we are reminded of the fragility of our vision, the limits of our models, and the beauty of a cosmos that will always remain partly unknown. So let us end not with certainty, but with reverence for the ghosts that drift between the galaxies, and the veils that drape the stars, for the silence that speaks, and the darkness that reveals. Let us carry these mysteries not as failures, but as invitations, to listen closer, to look deeper, to wonder longer, because beyond the reach of even our most sensitive instruments, the universe is still speaking in a language made of light and dust, signal and silence, knowledge and awe. And so we arrive at the end, or perhaps only the edge of the beginning, after venturing across ancient trails of stars and diving deep into galactic voids. After listening to the echoes of quasars and unraveling the magnetic tantrums of dying stars, we are left with something stranger than certainty's wonder. Not the kind of wonder born from answers, but from the realization that even the most precise instruments, the most elegant equations, and the most powerful telescopes are merely fingertips brushing the surface of a vast, unseen architecture. What have we found? Ghost streams whispering of ancient collisions, light bending to forgotten alignments, cosmic voids that repel galaxies like silent oars rowing through nothing, planets that refuse to radiate, elements that hide from our grasp, signals flickering from between galaxies, unclaimed by any known source, and dust everywhere, dust that dims and veils and guards the secrets of the stars. These are not just curiosities, they are messages. They are the universe leaning down and murmuring, "You do not yet understand me." But we try. With each anomaly, we expand the perimeter of the known. With each inconsistency, we are offered a portal into deeper laws. Science was never meant to be a fixed edifice. It is a raft in a storm, a melody played against silence. We do not map the cosmos to find comfort. We map it to remember that discomfort is a sign we are close to truth, that when a star vanishes without reason, or a polarization stretches across billions of light years, it is not failure, it is invitation. And behind all of it is time, time not just as ticking clocks or spinning orbits, but as a vast unfolding. These anomalies are fossils of motion, footprints in gravity, bruises left by forgotten giants. We are not outside this story. We are made of it. The lithium that should have been but isn't. The magnetar that screams once and dies. The rogue planet that drifts unloved through darkness. They are part of the same ledger that recorded your birth, your breath, your gaze upward on a cold night.